Okay, so second video. What have we done? We needed to define ourselves this little piece of charge because we're going to say that we're going to use the Eve equation for a point charge. And so we need to define some Q, a little piece of Q, but instead of summing up a whole bunch of little ones, we're going to actually use integration to then say to ourselves, okay, this is how much charge we have. And so we know we have a total Q, it's in a line, and we decided that that way we don't have to use like R1 and R2. We could just say a simple position coordinate on there, which would be alpha times, and alpha is defined from starting here at the x-axis going around. So the typical thing is then we have alpha times d alpha let me see. Let's make sure I do this right. So a piece of line is pi over 2, the whole thing, okay, it's pi over 2 times a, that's the whole length. We know that, so if we take the total Q divided by the total length, we get the amount of coulombs per length, which just happens to be, well, I just simplified it, 2Q over pi a. And then, so that means that if we want to find out how much charge is in d alpha, we know that a times d alpha, this distance right here, is going to get us the amount of charge. So it's not like I'm going from alpha 1 to alpha 2. I'm just simply going to say that I have a certain amount of d alpha. And of course, at some point, when we integrate, we have to make sure that the integration limits encompass that arc. Makes sense, right? So I put it all together. I double check my units. So I got meters, and then d alpha is some angle, but we have meters from A, and then we have Q time, the amount of coulombs per length, and it works out. In fact, A times d alpha is also in meters if I express d alpha in radians. Okay. And so that's going to be RTQ, the little bit of charge that we have. And so we can just rewrite it using lambda, A lambda d alpha. Just makes it a little easier, shorthand. And we are kind of anticipating that what's going to be our variable of integration. And so, which is going to be alpha. We're going to use alpha as our variable of integration. And the reason we're going to do it is because then we're going to have R be a constant value of alpha, of A, excuse me. Okay. So let's see what we got. So now, we've got an expression for our dq. So remember, we wrote out something earlier, dq. We have the k, and we have the r squared. So we see that we can say a, k, lambda, d alpha. I suppose I could put the k out front, over r squared. And to use our standard technique, let's insert a line. So we have our point of interest, we have our Q, And generally we'd just say that we're in the center of it. And so let's actually get back the both makes my, and then we want to just make that a dotted line. And then we see that, in fact, I forgot, that should be DE. And we have ourselves in our hat. Excuse me, in our hat. And let's say it's positive charge. So we have a DE vector. And yes, it is a vector. So that means that we do have to be a little careful when we integrate. Okay, so now we need an expression for R. And it just so happens that it's going to equal to A, or A equals R. And we like it because if we pick P, so we have to just make sure that we understand that the variable of integration, so at point P, we have a symmetry in this particular point P, and then that symmetry is that R of our DQs, or little q, are always equal to A. So this is a lucky thing. It's not that every problem we see is going to be like that. So then we see that our DE is now going to be equal to K A lambda D alpha times R hat divided by A squared. And it's a nice little bit that this cancels. And now, of course, in principle, we could just define a bunch of those. But we're going to now switch over. We're going to finish this up. And we're going to integrate. And, of course, we've had that in our minds all along because this is the DE, the DQ, and simply the fact that we said we're going to use calculus. So, I mean, it's kind of a no-brainer, right? So then we have, in fact, can I steal this picture here? Because I want to reuse it some. So I think what I want to do is I want to have this. And let's see if I can add these drawings into it. I'm going to pause for a moment. If you won't even know the difference. All right, so it kind of seems we have, and I suppose I could have copied it forward. So we have our DE equals to K lambda D alpha over A. And so we can do this integration. And these are constants. And we have D alpha. Now, again, it's simplistic because we're lucky to be at this point P. And so we can just make a limit of integration along here. But we have to, though, again, keep in mind that we have ourselves, and I suppose that goes outside, we have ourselves a vector. I'm looking at my notes at the left side. So we have to break this up into dE of x and dE of y at some point. Oh, in fact, no, right away we have to do it. So that means that dE cosine of alpha and dE sine of alpha, because cosine is the x-axis, so adjacent over hypotenuse, and opposite over hypotenuse, sine, the y-axis. Also notice this sign, if we do it all this way, there's no absolute value signs, and we have to remember to define alpha in this way. That will take care of all the plus and minuses for us. So then that means that E of x is going to equal to k lambda over a integral of cosine alpha d alphas. You know, so again, at the end of the day, these are pretty tame integrals, but you're generally given symmetry, problems that have some symmetry. And now, okay, what about our limits? What are our limits? Let's take a look. We have to figure that out. So I should have, woulda, shoulda, coulda. I forgot to duplicate the slide. Let's see what happens here. Well, okay, Control C. Gotta duplicate this slide, Harry. And let's paste. Oops, we got something. Yeah, we'll keep that. But for now, let's just duplicate that a few times just so we have it ready. I gave you a PowerPoint with lots of empty drawings like that. So our dE is, what was it, k lambda d alpha over a. All right, k lambda d alpha over a. And now we're trying to figure out limits. Okay. So remember, we were told that the total delta alpha is equal to pi over 2. And we were told that it was symmetric about the x-axis. And in fact, our diagram shows that. So that means that we have pi over 4 of it above and pi over 4 below. And this just happens to be pi over 2. And this happens to be pi. So that means that above the start point, alpha 1 is going to equal pi minus pi over 4, because this is the distance up to here. So one little trick is to just say 4 pi over 4, which is the same thing as pi, minus pi over 4, is going to get us 3 pi over 4. So this is alpha 1 equals 3 pi over 4. Now, we can do two things. We can just do pi over 4 below, or we could just simply say we need to go pi over 2 to get to alpha 2. So that's going to be alpha 2 is going to equal alpha 1 plus pi over 2, which is 3 pi over 4. And we'll change that to be 2 pi over 4. And that's 5 pi over 4. Okay. That's nice. Let's see if we can get a hold. I suppose we could try this lasso select. Now if I do the, oh yeah, control key. No. I have to do them both at the same time. Okay, let's see what we can see. Alpha 1, alpha 2. I don't know how to unselect something. So that's control C. We'll put it here. And so there's our limits of integration. And so now we need these two guys back. Let's see if we can lasso them. And I'll just add that control C. Control V. Oh, what a mess that is, huh? Let's put it up here. All right. So we got our integrals. We got our K lambda. We got that. Okay, nice. So we see, I'm looking at my next slide, and we're kind of ready to go here. So let's go ahead and let's duplicate that. Oh, I didn't want to do that. I want to duplicate the slide. Okay, so let's first do the X component. Okay, so first of all, integral of cosine is fairly straightforward. It's negative sine. No, give me a minute. Integral of cosine, the derivative of sine is cosine. And so integral of this is positive. Not derivative. Okay. And I'll cheat. Look at my notes. And let's see here. Pause time. I want this time actually to stop the video. And because it's already at 18 minutes. Okay, we'll stop this and I'll resume.